Lab 2 projectile motion. Table of contents. Introduction, projectile motion, then procedures, and analyze the data, explain errors, and answer the questions. Introduction. The purpose of this lab is to model projectile motion with and without drag and compare it to real-time data that was gathered in class by video. In this lab, I used the principle of gravity, which is a force that is caused by Earth's pull. The object used was a wadded and crumpled piece of paper. Used tracker to observe the actual position, and the calculated position was calculated with glow script. The results were the model data with drag produced a squished parabola. Without drag, it produced a perfect parabola, and the track data was a parabola in the middle of those, so it had a mix of the characteristics. Not too parabolic, but not too squished. Projectile motion. Projectile motion is 2D motion that occurs when an object is launched into the air and is only influenced by gravity. In real life, drag is the force opposing the motion. In a perfect world, drag is neglected, leaving gravity to be the sole force on the object. Some characteristics of a perfect world are constant horizontal velocity, and the vertical motion is influenced by gravity. These equations, except for the bottom right, are all equations used in perfect world projectile motion problems. On the bottom right equation is actually the force of drag, which is incorporated into real world projectile motion problems where you have to take into account the air resistance. The procedure was measured 1 meter on the whiteboard in the background and measured 1.5 meters off the ground. Then I recorded a video of my classmate throwing a crumpled piece of paper in a parabolic path. Then imported the video into Tracker and tracked the position of the paper frame by frame. Next was creating a computational model of the projectile motion on GlowScript using the roughly the same time interval, and found the initial velocity for the model using the initial position and time values of the first 2 frames. I experimented with different B values until I found the right one, and I created a spreadsheet with all 3 graphs, and then I graphically compared them and made conclusions. So this is the video of our crumpled piece of paper. The tracker analysis, the delta time was approximately 0.035 seconds. The initial x velocity was about 4.46 meters per second, and the initial y was about 2.11 meters per second. So the computational model, the while loop ends when t is less than 0.721 seconds. F net, so total force equals force of gravity plus the force of drag. As you can see on the right, that is shown, and all 3 of those forces are defined. And then to visualize the drag and gravity arrows, I had to multiply and divide by vectors to exaggerate them. So you can see the gravity arrow was, the vector was divided by 9, and the drag arrow, the vector was multiplied by 10, just so the arrows are exaggerated and they're not too small or too big on the screen. So continued, mass does not matter in an ideal world. However, when drag is accounted for, it does matter. The initial velocity on the right is initialized in a vector, and delta t is set to the time between each frame, which is 0.035 seconds. And then b is equal to 0 for the real perfect world simulation, and it's set to 0.005 for the drag simulation. The GlowScript output on the left is of perfect world, which you can see it's very parabolic, and it actually goes the furthest x distance. And then on the right, it goes less x distance and it's more squished. And you can see the orange arrow on the right is actually the force of drag opposing motion. The velocity versus time, no drag, x horizontal velocity is constant, and y is constant acceleration, and then with drag, both are non-constant velocities. The observers predicted on the same chart, you can see the orange is more parabolic than the other 2. With drag, simulation is green, and you can see it's more squished, and then the tracker data is actually, it's a little bumpy, but it's actually not as parabolic as the first one, but not as squished as the green one. Some possible errors were the graphs ending at different y values. So on that graph earlier, you can see that they did not end at the same y values, and this is due to the way the while loop uses the set time interval. So if the while loop is set to end also when y equals 0, then it would be consistent among all 3 graphs. Second error was tracking issues when using tracker, so position values that were not tracked, or that were tracked, were not very smooth. Third error was rounding errors when calculating the time interval and or velocity. And then the final one is exaggerated or too small of drag force. So that could be due to an overestimation or underestimation of the b value. So questions. Terminal velocity was shown by the curved and plateauing nature of the drag velocity graphs. But to fully know if there is a terminal velocity, I'd have to conduct an experiment where the object is in the air for longer. And for the second question, the time for the object thrown straight up will take longer to come down because all of its velocity will be in the y direction instead of split between the x and y directions like our experiment. If the velocity in the y direction of our experiment was the same as this hypothetical, then it would be the same amount of time. Thank you.